So this is section 5.4, which is called work. And there's still the aspect, because this is chapter 5, on adding up an infinite number of slices, so like volume, but in the context of work. So the formula for work, and what work is it's basically what you get when you move an object a certain distance with a constant force. So work is just force times distance. That's all that work is. Okay, so notice the multiplication there. As a very basic example, we have find the work done by lifting 10 kilograms of weight from the floor, basically up a half of a meter. So it's literally just what is the work done to lift this thing up, and it's going up half a meter. So the first thing that we'd have to think about is actually finding the force. And force is mass times acceleration. Now this is notice this is in metric units here. So we want to understand that acceleration is 9.8 meters per second squared. Again, that's a metric, using the metric system. And we have our 10 kilograms, our weight. So the force is mass times acceleration. And what you want to see is when we have something in kilograms or in metric units, we need the acceleration in order to get the force. However, I want to make a note here that when we see things in pounds, so our system in the United States is pounds, so pounds are a unit of force. So what that means is if you're given something in pounds, so if I were to ask the same question, but I was to say find the work done lifting 20 pounds from the floor to a 3 feet high bench, and I have everything in R units, then I don't need to multiply by acceleration, because for pounds, they are already a unit of force. So it's already the mass times acceleration is being done. And what another example of that is, if you were to go to Mars, for example, however much you weigh here is different than how much you weigh on Mars. However, your mass is the same. We'll see more. Okay, so pounds are a unit of force, and so for this, when you see stuff in your US units, work is in what's called foot pounds. That's actually the units for work if you're in the system for the United States. Now, in terms of force for the metric system, it is this is newtons. That's the measure. And if you end up doing stuff in physics, you'll see a lot more of this type of thing. We just see this section here. So that's newtons, and then work is force times distance, just like we saw up here. So still force times distance. It's just that force is taking your newtons and multiplying it by the distance, how much you are, in this case, lifting, how long, what the distance is. And that units is this J, and that is joules. So our focus will be probably a bit more on the US side, pounds and foot pounds, but understand that you could also be thinking about newtons and joules if you were thinking about the metric system for work. All it is just different units for different systems. So the actual work done by a force is the idea of integration here. So that's why it's in this chapter. But you've got your variable force, that's what's considered your function, your f of x, and it's moving an object along some sort of axis. So we might say the x-axis, but it really just depends on, because we can orient things any way we want. But in this case, notice it's just the integral here from a to b of f of x dx. That is the work that is done. And So let's kind of look at what that means. So what we really want to see here is it's still the same idea of everything that we've been talking about this whole chapter, which is the idea of splitting into subintervals, and in this case like little slices, and then adding up those slices together by doing some sort of multiplication of a height times a length. And we just see that in a slightly different way because of work. And it still comes out to be, you know, this idea here that you're adding up some infinite number of the slices. Okay. So I'm going to write a couple notes on the side. So when you see this notation foot-pounds, the definition of foot-pounds is the work done by 1 pound of force acting through a distance of 1 foot. Okay, now, and I'm going to make one more note, but I'm going to make it down here so that it doesn't get in the way of the camera. I'm going to define what a Newton is. So a Newton is the force required to produce an acceleration of 1 meter per second, that's acceleration, on a mass of 1 kilogram. So here's our first example. A cable that weighs 3 pounds per foot, so understand that we're talking about US units here, is used to lift rock up a mine shaft that is 40 feet deep. Find the work done in lifting 250 pounds of rock to the top. So the idea here is you have this cable. Now this cable is a variable force, and that's because depending on how much of the cable is down and how much of the cable is up, you know, it weighs less. And therefore, you know, imagine like pulling something up to, you know, the top of some space. You'll find that it's harder in the beginning because you have so much more that you're lifting up. And then of course, as you pull it, it gets a bit lighter. So that's a variable force. However, this piece right here, this, you know, rock that we have is a constant force because it's always there and it doesn't change because you're bringing it up from the bottom. So you have a constant force here and a variable force. Now, the way we want to think about this, the easiest way is to take a look at this whole distance that we have. And then consider the fact that the mine shaft is 40 feet deep. So we're just going to kind of think about it like this. Now, of course, remember that when this starts, this piece of this rock thing is down at the bottom. But this whole thing is 40 feet deep up till the top. And so if we call this distance x, then this distance here would be 40 minus x. So this helps us because it's talking to us about the distance of how much we're moving this, you know, this rock. So let's think about, when we think about the slices, what we have here is a slice of cable. So you want to think about like a little slice of this cable here because you're basically adding up an infinite number of those as they get thinner and thinner. So the slice of cable is 3 pounds per foot, okay, because that's how much it weighs, 3 pounds per foot. And just depending on how thick your slice is, that's this idea of the change in X. So when you think about how thick that cable might be, you can just think about your slice being some sort of delta X. You don't know exactly, how thick it is, but it gets thinner and thinner as your slices get thinner and thinner. So that means that the weight of any slice of cable, as you can see, is just 3 times delta X pounds. That would be the weight of any slice. And that makes sense. So the work needed to bring this cable up, and then as well as the rock, is the distance, which is 40 minus X, because that's wherever it's at in the cableness, and then times the weight. So there you go. Okay, now this is coming back from the first page. If you look at the first page, we're talking about work being force times distance. So that's where this is coming from. That's how we ended up with this piece. However, this is of course not, we don't have it yet because we actually need to integrate this. So that's just for one little slice there. So you want to think about the fact that everything is going from the bottom, this rock is going from the bottom up to 40 feet. And what we're doing here takes into account the fact that some of the cable is already almost at the top and some of the cable is almost at the bottom. But to do the whole thing, we're going to go from 0 to 40. So that's lifting up the 40 feet. And then we can put in what we've created here, 3 times 40 minus X, the work needed. And then of course, instead of delta X, I'll have dx, like that. And then the other thing, so what I really want you to see before we evaluate this is that what this piece is just the work for the cable. And because it's a variable force, that is why we need to use the integration. However, I'm going to add an addition sign at the end. So notice this is not included in the integral. And when we think about what we need to do to, do the work for that rock, it's going to go 40 feet because it's down at the bottom, and it's 250 pounds. And because remember, when we have pounds, that's already a unit of force. So this is force times distance here already. It's going 40 feet and it's 250 pounds. So that's just a separate piece that we don't need to integrate or do anything to, but that would just be what would be required for something that has the constant force. So this is the work for the rock. So now we have that. So now all we need to do is just integrate and add our values together. So at this point, it's fairly straightforward here. So we will have the integral, and that 3 can be on the outside, of course. The integral of 40 minus x dx is 40x minus x squared over 2. That's being integrated from 0 to 40. And then this extra piece that we have on, it's just a multiplication, and we get 10,000. Then I'm going to move it just a little bit over here just for the video. So now we'll just evaluate. So we'll have 3, and then we put in 40, and that's going to give us 1600 minus 800. And when we subtract, we're plugging in 0, and that's nothing. And then we'll still have our 10,000 at the end. And so just evaluating that, we'll have 800 times 3 plus 10,000. So we're going to have 12,400 foot-pounds. And so that's the work required to lift up the cable as well as the rock. So you can kind of see that the cable itself is only 2,400 foot-pounds. But by adding that rock, that's the extra 10,000 just to bring that up from the bottom as well, because it's sitting there on the bottom and now has to be lifted. So let's look at some more examples. We've got a cylindrical tank. It has base with radius 2 feet, and it has a height of 12 feet, and it's sunk into the ground. So our job here is to think about that it's in the ground. Okay, so here we are. That's the ground right there. And the tank contains a liquid that has a density of 80 pounds per cubic foot. So that matters because force is going to be affected by the density of a liquid. So it'll take less work for like water than it would for something that has like a higher density, like oil, things like that. So it has to be taken into consideration. And no, I do not expect my students to know the density of things. That will always be given to you. So something we want to remember is that the volume of any cylinder is pi r squared h. And what we want to think about always is the volume of a slice. So we want to think about, if we, very similar to the last problem, if we break this apart, we want to think about the fact that, and again, it doesn't really matter how you break it apart, you're just thinking about the fact that if one distance is x, then your other distance, in this case, is 12 minus x, which is important because you're thinking about how much you're, bringing up something essentially to the surface. Well, we'll see what the problem tells us. But we're thinking that here x equals 0, here x equals 12. So even though it's a vertical distance, it's not really relevant in terms of the idea of the limits of integration. We can integrate from 1 to 12, and that's still going to give us what we're looking for here. Variables are arbitrary, but students like x. So in terms of the volume of a slice, we want to think about the fact that each slice, so if we were to think about a slice of this cylindrical tank with this liquid in it, so you're just thinking about, one slice here. More or less. So you want to think about the fact that the volume of it is still pi r squared h because it's still just a little cylinder, but the height in this case is the change delta x, because that's what this is right here. Delta x is, its height because of the fact that we're using x as our variable. So what that means for us, knowing the radius of the cylinder that we have, that is 4 pi times the change in x. And that units is feet cubed because it's a volume, so it's feet cubed. Now, the reason I say that is because now we want to think about the weight of a slice. And the weight of the slice, and the weight of any slice, and this is something to note, is that it's density times volume. Density times volume. So our density times our volume is going to give us our force. So we have 80 pounds per feet cubed. That's been given to us by the problem. And then we multiply that by our volume, 4 pi delta x times feet cubed. The reason I do this is because I want you to see that the feet cubes are gone. And that's important because what that's telling us is that we have 320 pi times delta x, and that is in terms of feet, or pounds, pounds. And pounds is a unit of force. So if you can get yourself to the point where you have pounds, then you know you have your unit of force. And because we're just looking at force times distance, we're ready to go at this point. So for A, it says find the work done to pump the liquid to the surface if the tank is completely filled and the top of the tank is at surface level. So that's something to think about because, of course, if it's not filled completely, then you wouldn't have as far to go. Things like that would have to be considered. We'll look at another example. But in this case, we're taking it from, it's completely filled and we're taking it all to the top. So we're going from 0 to 12. And our distance here is similar to the cable. We're going 12 minus x because it's wherever x is where we're at in the tank. 12 minus x, and then times what we just found here, which is the 320 pi times delta x. And of course, what we can do, if you want, very simple, you can pull out the 320 pi because that's just a constant, and that delta x is your dx when you integrate, because you're doing that infinite number. So now that we have that, it just becomes a pretty straightforward 320 pi times, and then we take the integral of 12 minus x with respect to x, so that's going to be 12x minus x squared over 2. And then we're integrating from 0 to 12, so not too bad because we have that 0. And so that just ends up being, I'll put it here, 320 pi. And then when we put in 12, we get 144 minus 144 divided by 2, 72. So it looks like we will have, when you multiply that out, 23,040 pi. And that is, again, the units there are foot-pounds. And so that's our answer for A. And now I'll show you B because it's only just slightly different. So I'll show you the differences, but we're still using a lot of the pieces here from this page. So for B, notice the only difference is that the tank is filled to a height of 10 feet. And the top of the tank is 3 feet below the surface, but we're trying to get it to the surface. Okay, so now our surface, I've created another picture here. So you can draw another one if you want, but here's the surface. So we want to understand that now our tank is still 12, but we also have this distance, which is 3. This is the same tank, so it still has the radius of 2. So we want the liquid to go all the way from the bottom to the surface, but it's only filled to a height. So right now the tank is only filled to here. So it's not filled to the brim, it's not filled to 12, it's only filled to 10. So that's just something we have to consider as well. Okay. However, a lot of this is all still the same. So the distance is now, instead of 12 minus x, we're thinking about the fact that it's got to go all the way up 15. So now when we call this x, this is now 15 minus x because it needs to go the 12 plus another 3. So our distance here is going to be 15 minus x instead of 12 minus x. So that's a small difference. And then the work here required is, we have our 15 minus x here, so I just want to show you the parts that are the same, 15 minus x, and we still have the 320 pi dx, so that's all the same. But in terms of where we're going, we went from 0 to 12 because we were taking 12, feet of a height of a cylinder up from the bottom to the top. But now we only have that 0 to 10 because we're only filled to 10. So this thing here, let me put this in red as a tip. These limits of integration here, what matters is, how did I say this? I say limits deal with how filled the tank is. So notice that difference. That's why we have 0 to 10. Otherwise that, everything's, very, very similar. It's still a very straightforward integration here. We'll put the 320 pi on the outside. We're integrating that inside, so just 15 minus x, so it'll be 15x minus x squared over 2. You're welcome to pause and see if you can do it. We're integrating from 0 to 10. So very small difference here. We'll have 320 pi. We have 150 when we put in 10 minus 50. And when we put in 0, we get nothing, so helpful there. So you can see that that's going to give us 320,000 pi and 32,000 pi. What did I say? And that is, again, our foot-pounds.